Okay, welcome back. This is the fourth video in the playlist that deals with making equilibrium calculations, and it's part of the general playlist in the area of chemical equilibrium. And what we're going to do in this problem is solve a chemical equation for the equilibrium concentrations of a particular reaction where the equilibrium constant is considered a small value. So notice that the Kc here is 1.1 times 10 to the minus fourth. And it's a small value because it's far less than 1. So if you remember back to the early videos in the playlist on equilibrium, I raised the issue of the free energy. And so if I just review that for a second, we can draw a number line here where I represent the different options for free energy for a chemical reaction. And in the case where delta G naught is a large positive value, in this realm out here, this is where your K values are small. They're much less than 1. And the key thing that's going to help us solve this particular problem is remembering that when the equilibrium constant is a number which is much less than 1, then once equilibrium is reached, the concentration of the reactants are much greater than the concentration of the products in the reaction mixture. And that's going to be a very important point that we're going to have to utilize in order to make it convenient to actually solve this problem. So let's now lay out what the problem is. So what we're going to do is we're going to combine 0.99 molar of bromine with 0.96 molar of chlorine initially. And like in the previous problems, we're going to set up what we call our ICE, which stands for initial change equilibrium. In my classes, I call this the box. And so we're going to set up our box here. And when I set up my ICE, I use the word before to indicate what the condition of the reactants and the products are before the reaction reaches equilibrium. So we're initiating this reaction with 0.99 molar Br2 and 0.96 molar Cl2, and there is no BrCl, so I'm going to insert a 0 in my box. Now, after the reaction comes to equilibrium, what we're going to do now is show how this change has to occur. And since there's no BrCl to begin with, then the reaction has to shift to the right in order to produce some BrCl. Keep in mind the equilibrium constant is small, and therefore the delta G for this reaction is going to be a large positive value. And what this means is that the amount of BrCl that we produce is going to be a very small value. So in the box, the way we're going to show this transition is the Br2 is going to have to decrease by a small value, and the amount that it decreases is based on the coefficients from the balanced equation. Notice that there is a 1 in front of the Br2 and a 1 in front of the Cl2. So the change that occurs for the Br2 will be minus x, and the change that occurs for the Cl2 is also going to be minus x. The change that happens for the BrCl, since the coefficient is 2, is going to be 2x. Now, let's go ahead and set up our equilibrium expression. And like I've done in previous videos, I always rewrite my expression without inserting the numbers first. So the Kc is going to be equal to the concentration of BrCl, quantity squared, over concentration of Br2 times the concentration of Cl2. And each of these is raised to the first power based on the coefficient. And remember, the expression comes from what we call the law of mass action. Now, we'll go ahead and insert the numbers. So my Kc value for this is 1.11 times 10 to the minus fourth. The concentration of BrCl at equilibrium is going to be 2x. Quantity squared. Okay, and this is going to be over 0.99 minus x for the Br2 times 0.96 minus x for the Cl2. Now, when you inspect the expression that we have, you can see that in the denominator, these two quantities are not the same. So if we were to carry out the algebra right now, we're going to have to solve a quadratic equation. And that's the part of this that's really inconvenient. And I've done at least one example where we had to use the quadratic. But if we can, we'd like to avoid that because it allows us to solve the problem more quickly and more efficiently. Now, in this case, since we have a small equilibrium constant, we actually can use a trick to do just that. So here's what the deal is. I've already introduced the idea at the beginning of the video that we've got a small equilibrium constant, and what that means is that the free energy change for this reaction is a large magnitude number that is positive, and that means that our K value is much less than 1. And what that means in reality is that at equilibrium, the concentration of reactants is going to be much, much higher than the concentration of products. And what that means to us in this particular type of problem is that the change that occurs here between the initial concentrations of our two reactants, the amount that these concentrations decrease is going to be very, very small by comparison to the starting concentration that we have in the first place. So what we can do is we can neglect the x. So we're going to come into these sums, and what we're arguing here is that when we subtract this x value from 0.99, the amount that 0.99 is going to actually change is going to be small enough that we can ignore the x. So we're going to pull both of the x values out of the sum, and I'm going to rewrite my equation the following way. So I'm going to go ahead and carry out the numerator. It's 2x quantity squared. So in the top of the fraction, we're going to have 4x squared. So I'll go ahead and write it that way. And then in the bottom, we're going to have 0.99 that represents the Br2, and the 0.96, which now represents the Cl2. So what we've done here is we've made an assumption, and we're assuming, because the equilibrium constant is so small, that we can neglect the x value that we're subtracting from the initial concentrations of both reactants. Now, we have to test that assumption. We're going to go ahead and we're going to solve for the x, and then we're going to have to test the assumption two ways. So first, let's solve for the x, and then I will teach you about the two tests that we have to carry out in order to make certain that the assumption that we made here that allowed us to drop these sums was a valid assumption to make. So let's go ahead and solve for x. And what we're going to do first is multiply the 0.99 times the 0.96 in the denominator, and then multiply it times 1.11 times 10 to the minus fourth. So the new expression here will be 4x squared, which is going to be equal to 1.05494, and I'm just going to carry my numbers out all the way on the screen of my calculator, and then this is times 10 to the minus fourth. Alright, and then dividing both sides by 4, my x squared value now is going to be equal to 2.63736 times 10 to the minus fifth. And now we're free to take the square root of both sides, and the x value that we're going to get, let me just put these brackets in to make sure that I don't lose anyone here. So we're square rooting both sides of my equation. And my x value is going to be 0.00514. Okay, now we found our x value without having to use the quadratic formula. And what we need to do at this point is test this to make sure that we made a valid assumption in the first place that allowed us to drop these sums out. So the first thing that we're going to do is what's called the 5% rule. And what the 5% rule states is that x must be less than 5% of the initial concentration of reactant in order for the assumption to hold up of reactant. Okay, so let's do that test first. And the value that I'm going to use to do the test is going to be the Cl2 because it's actually a smaller value than the Br2, so to be on the safe side. So let's go ahead and test our values. So 5% rule. All right, and our x value is 0.00514, and we're dividing that by 0.96 times 100. All right, and when we go ahead and run that calculation out, we see that we're at 0.54% of the total. 0.54%, and obviously this is well within 5%. So that's the first test that tells us it was okay to eliminate the sums that we had up here in the starting equation. Now let's go ahead and calculate the concentration of each respective value now. So Br2 is going to equal 0.99 minus 0.00514. And when we run that, it's going to be equal to 0.98486 molar for the Br2. The Cl2 similarly is going to be 0.96 minus the same value, so x is 0.00514, and so the molarity at equilibrium of the Cl2 is going to be 0.95486. Now, the concentration of the BrCl is going to equal 2 times the x value, so it's 2 times 0.00514, and that's going to equal 0.01028. Now, what we need to do as a second test is calculate Kc nu using these values. And if our assumption was correct, then the new Kc that we get, our new equilibrium constant, should be very close to the actual Kc. So I'm going to calculate quickly my Kc value, plugging in my values that were approximated using this technique. So the BrCl will be quantity squared here, and then this will be divided by the new concentration of the Br2. And the new concentration of the Cl2, and the value that we get is 1.12 times 10 to the minus fourth. And you can see that there's a really nice correlation between that and the original Kc value that we were given at the beginning of the problem. All right, now to finish the video, there's two things that you need to be aware of when you're going to use this technique. So way back here at the beginning, when we made the decision to neglect x, all right, so to neglect x, you need two things. You need a small k value, and usually what I tell my class is that small k is any value that is 1 times 10 to the minus 3 or smaller. Okay, and the second thing you've got to have is a reasonably large initial concentration of reactants. All right, and in a subsequent video, I will do an example where I show you what happens if we decrease the concentration of the reactants to some threshold value. So for now, before I sign off, to emphasize what I mean by this second thing here is that if we were dealing with a concentration of Br2 and Cl2 that were, say, 0.0099 or 0.0096, then there's a good chance that this approximation that we made here would fail. So the two things that you've got to pay attention to are, do you have a K value that's small? If it's 1 times 10 to the minus 3 or smaller, then the answer is probably yes. And then secondly, you need to look at the concentration of the reactants that you were given, and they need to be reasonably large, somewhere around or close to 1 molar. And if they're less than that, then you should expect that you may have problems when you go and to calculate the 5% rule. And with that, I'm going to go ahead and sign off.